So, welcome to the lecture course on quantum gravity. Today's topic is Chapter 4, the Hamiltonian formulation of general relativity. Just to briefly recall, in Chapter 3, we discussed reparameterization in invariant systems, the parameterized non-relativistic particle, relativistic particle bosonic string, and then also parameterized field series. With an eye towards, the real thing, which is general relativity. And with this preparation, I think we can now really dive into the Hamiltonian formalism of general relativity. It's not yet quantum gravity. This will be done next week, next Wednesday. But today we make the formalism, the classical canonical formalism of general relativity. So I briefly mentioned last time that you can find this by a different route, a so-called seventh route to geometrodynamics, just from the algebra of the constraint. And if you want to realize them in a space-time, these hypersurface deformations, assuming that there's only the metric as a dynamical variable, not other geometric quantities, then you can also arrive at general relativity. Now that's very interesting, but would maybe lead us a bit too far away from the main line. And for those of you who are interested, you can read this in the book or in the original article by Hochmann, Kuhas, and Teitelbaum. Now, why do we want that? No? We want to have a formalism where we define canonical momenta. In mechanics, it's just a derivative, the Lagrangian, with respect to q dot, and then we have Poisson brackets between the p's and the q's, and we want to take them into commutators and introduce therefore h bar and realize the commutators on an appropriate space of wave functions. And the covariant formulation of Einstein theory is not in this form. So in Chapter 2, we had this covariant quantization, which is the path integral. You integrate over all four-dimensional metric configurations weighted by e to the I times the Einstein-Hilbert action over h bar. But the alternative is to have here something like Schrödinger formulation or wave functional formulation, as we did in Chapter 3. And this is why we have to split up space-time in order to define this. So today I will derive actually what the q's are here in Einstein theory and what the p's are. And we will have then the canonical relations between p's and q. Next week then they will be turned into commutators, and then we will apply them on wave functionals and discuss really quantum gravity with it. Now, to do that, we have to unfortunately break up the nice covariant structure of four-dimensional space-time. In general relativity, you have learned that space-time is given by a manifold. Let us restrict to 4 dimensions, which is the usual thing, and the four-dimensional metric. But here we have, because the Hamiltonian usually translates or transforms between different times, which is here different three-dimensional hypersurfaces. So we have to split this up into a foliation of hypersurfaces. And for that we assume that we can do that, that the space-time is such that we can have really a foliation into space-like hypersurfaces without singularities. So the technical term for that is Cauchy hypersurfaces, no? So that we can really have, like in flat space-time, you have a space-like hypersurface from where you can put initial data, and then the whole evolution is determined. And in geometry, it means that M is of the form that one calls globally hyperbolic, or in mathematical language, it can be written as a direct product between the real numbers, which stands for time. So this runs just from minus infinity to infinity. There are no for example, no closed time-like world line, so that you can travel via your future into your own past. And sigma is a three-dimensional manifold, which can be arbitrary at that point. So this is globally hyperbolic. And this is nice in many ways, because the usual field equations that you have, whether it's then Einstein's or maybe of other fields, we have a well-defined initial value problem. So that's globally hyperbolic. It's also equivalent to what Roger Penrose defines as strong cosmic censorship. So this corresponds to strong cosmic censorship, which means that no naked singularity are there. Actually, no singularities at all are here in that strong version, so no visible singularity. The weak version is the asymptotic predictability, so there are maybe naked singularities, but as in Kerr, they are hidden in the horizon. So you may call this a disadvantage because it fixes the topology of space-time, and there's a in a sense a dispute among in the community whether this really is restrictive or not, because in the path integral you could integrate over other manifolds also, but it's not so clear whether this is really allowed in the formalism. Anyway, in the canonical formalism, that's the assumption. That is, you fix the topology of sigma. For example, it can be a three-sphere, it can be a three-torus, it can be a Klein bottle, and for each such choice you have a different theory, in a sense, a different formalism, not a theory, a different formalism. I should mention, and this is very important, that this is also the assumption made by people working in numerical classical relativity, because they also like this formalism. They're not interested in quantum gravity, but in numerical relativity, you usually are not interested to find the full space-time at once in one solution. What you want to do is, for example, you want to have, say, two neutron stars that coalesce around each other and emit gravitational waves. And so you want to have an initial condition, say the two stars at some distance, and then putting this to the computer, and the computer should then produce how they spiral into each other and emit gravitational waves. And also for that to work, you need this global hyperbolicity, because otherwise, the computer, if there's no unique answer to the initial values, then the computer does not know what to do, right? So you must know that you put in initial condition, and the computer produces you the evolution. Here I have already depicted a picture similar to the one last time. So I have, I split up space-time into, it's also called 3+1 formulation, because this is three-dimensional and this is one-dimensional, and have here one space-like hypersurface at a coordinate time t, and other one at a coordinate time t plus dt. And then I can choose freely spatial coordinates here. They are xa, a, 1, 2, 3, and the xa is somewhere here, and we connect this, and we call this t mu, the vector t mu. Everything is proportional to dt because it's infinitesimal. And this t mu, nabla mu t, is 1. It's also called the flow of time, somewhat metaphorically, but it's just the time coordinate. And instead of going there directly, you can first go on the sigma t until you hit a point that when you connect this orthogonally, you are here just below this xa. So you have here this distance, which is given by the lapse function and the normal vector, and here you have the tangential vectors. Last time we had this with na x mu comma a, but we can just call this the shift vector because it's in 3 dimension. So you can literally think, first we have to walk here on the 3 space somewhere until directly above us, we have the same coordinate value on, say, the ceiling is the neighboring hypersurface. So these are lapse and shift, and these are four quantities, and they will become they are part of the four-dimensional metric, and they comprise the part that you can choose freely in a sense. Yeah, because you're free to choose your foliation, you're free to choose your coordinates on the hypersurface. Now it's clear that mu is normalized here to -1. Now let's define here a quantity that we identify as a three-dimensional metric. First, it has here four-dimensional indices, but it will have the properties of a projector. So if we define this as the space-time metric G mu nu plus N mu Nu, then this defines a three-dimensional metric. Why? Because if you contract this with Nu, then you get 0. No, because here, yeah, you can see that. I mean, this gives -1 and this gives N mu. So it's orthogonal to this, so it lives here in a sigma. And if you apply it twice and sum here over nu, then you get again H mu rho. Another property is that the trace is 3. No? So this is the property of a projector. So you project onto a three-dimensional hypersurface, and if you apply it twice, then okay, nothing new happens. Below, we will always label this with HAB because of this fact. This is a quantity that only lives in the three-dimensional slices. So we could, of course, write this in a four-dimensional way, but because of this projector identity, we can immediately go to 3 dimensions and just label it by spatial indices. So later or below, it's just HAB. And this is a general property. I mean, there is an isomorphism between tensor fields that live on the full manifold and that are orthogonal to this normal vector on each index, and tensor fields on sigma. No? So if you have any tensor field with space-time indices and with respect to every index is orthogonal to N mu, then you can directly map this to a tensor field that is on the three-dimensional space only. So you can forget about, say, just the four-dimensional formalism. Now this T mu here, I mean, infinitesimally, you can write as n times N mu plus N mu. I mean, with this the lapse, and this the shift. And the shift is demanded to be purely spatial, so N mu times N mu is 0. So it's orthogonal to that. And this is why we can identify it with a purely spatial quantity. You know, we don't have to consider a time index of that. And later we always write NA. We don't never write mu. It's just for the beginning, because you start with a four-dimensional formalism, and so somehow I must convey to you the picture how to project these things down. Now in the last section, we had here NA times x mu comma a. There I had this embeddings, so that would correspond to what we did last time. But here I directly go to the space-time metric. Also last time we had then the line element, so also in paragraph 3c, so we have G mu nu dx mu written as minus n squared dt squared. No, that's the part here. And then we had HAB, and now I really use the spatial notation, and dxa plus ne dt dxb plus nb dt. No? So here that's clear to go to here, but because here you have the infinitesimals, of course, you go to some neighborhood here, xa plus dxa. And this you must add here in addition to the pure shift. Yeah, so then to summarize, then we can write a four-dimensional metric as follows if we have a matrix notation. So the 0, 0 component, this is here, you get here the dt squared from here, but you also have here dt squared. Now if you multiply this out, so you get here not in the 0, 0 component na minus n squared, and we have here nb, nc, and here we have hab. No? I mean, this stands formally, I hope the notation is clear, for n1, n2, n3, and this also for n1, n2, and 3. It's just formally written down with an index. And I should say that nb with lower index is h, bc, and c. So because this is the three-dimensional metric, we can raise and lower indices in 3 dimensions with HAB the same way as we can raise and lower indices in 4 dimensions with G mu nu. And of course this here is positive definite by assumption. No? Time is only this part, and space has signature plus plus plus. 3-dimensional Euclidean signature. Now the inverse is of course also important for calculation, and you can check by just multiplying then the two that the following is the inverse. You have minus 1 over n squared. You have here nb over n squared, nc over n squared, and here you have the inverse of the 3 metric, but in addition some term which includes the shift minus na and b over n squared. Yeah. So you can, by calculating g mu nu times g nu rho, convince yourself that this gives just 1, I mean the delta function. Yeah, so you see here this is the inverse of the 3 metric. I mean HAB times HBC is delta AC. But the spatial part here of the inverse space-time metric is not the same as the inverse of the space metric. Only if you choose the shift equal to 0. As you can do, no? This is a particular coordinate system, but then you would give away the freedom. I mean, if you choose this from the very beginning, but you could do, and then you just had here the inverse. But otherwise, they are here. So that's very important. Because of that here, we can introduce the one form for the normal vector, so the normal one form. Let me call it n with a lower tilde, the one form, which is n mu dx mu, and which I choose to be minus n dt. I mean the minus because of the signature of the space-time metric, which has a minus in the time part, because then we get for the normal vector mu, which is g mu nu, and mu we get, this is n to the minus 1, we get here a positive sign, minus n times n to the minus 1. So the n vector means n1, n2, and 3. I hope the notation is clear. Otherwise, please ask if I do something that you do not understand. Also that's the vector, and the more geometric quantity is that one form from here, because it's just proportional dt, and so the vector itself looks a little bit more complicated. Yeah. Now the various hypersurfaces that we have here, sigma t plus dt, they can be identified with each other by, we are identifying here points that are reached by this flow here. So instead of having, say, infinitely many sigmas with each with a 3 metric, we can imagine there's just one sigma and a time-dependent 3 metric. Yeah? Yeah? Is it clear that these are equivalent picture? You can have all of these, and here the age and there the age, or you can have one sigma and identify, so to speak, all these points. But then, of course, the metric on all this is time dependent because it's different here and here. So, and this is the usual canonical viewpoint that people have. So the usual point is, okay, you make this foliation first, but then the formalism, you think about one sigma, a manifold, and on it that metric that depends on t. So the various hypersurfaces sigma t can be identified by a diffeomorphism that is generated by the integral curves of T mu. Yeah, you have this flow of time that connects everything, and you can then go from here to here, and here to the next, and here to the next. And this gives you a diffeomorphism between all of them. And so you have one sigma and a time-dependent metric. So identify M over G, which is globally hyperbolic, otherwise this would not work. Globally hyperbolic, as the time evolution of a Riemannian metric HAB of T on a fixed manifold sigma. No? That's the picture. And you may say, okay, this is equivalent, so we can view it one way or the other, but there's a reason why this is superior. Why? Because you do not yet need for this to solve Einstein's equations and think about the solutions. This concept already exists before you think about classical solutions. And then, as you will see next week, in the quantum theory, anyway, we have no classical solutions. We have no space-time, no classical space-time. We have something quantum. So this is much more tailored to the conceptual picture also of the quantum theory than having the classical space-time with solutions of Einstein equations and having this foliation. So you don't need any embedding for that picture. No need for any embedding. So you somehow liberate yourself from this picture of that you already have a space-time that is a solution to Einstein equations and that we just rewrite. Although classically, if you only do classical physics at the end, they are equivalent. So this, because the space-like hypersurfaces, they represent a fixed time t, if you like, it's clear that the role of the position coordinate q in mechanics is here played by the three-dimensional metric HAB, not the four-dimensional metric, because that's what is defined on sigma, and HAB of t would be the evolution of that, like q of t in mechanics. So HAB is the dynamical variable. That corresponds to the Q's. So we have then to find the P's, and then we have at least the kinematics. of course not yet a 9. No, so that's, I think, the important insight by these people like Dirac and Arnold, Deser, Miesner, and so on, that the dynamics here is in the 3 geometry and not the 4 geometry. The 4 geometry, in addition, contains these things, lapse and shift, that you can somehow choose at will, and yeah, it has this coordinate freedom in it. So let's look for the conjugate variable. For this purpose, I define another tensor field. Also, again, first in space-time, and then it will also be shown to be purely 3-dimensional, and then it gets space indices. But for the time being, let us have in here a k mu nu, and define this as h mu rho nabla, the covariant derivative with respect to the space-time metric of the lower index n. Unfortunately, in the literature, you find sometimes this with a minus, this definition. I cannot change that. It just means you must be careful if you read literature, whether you go to Miesner, Thorn and Wheeler or to Wald or so. That's how it is. No? We can, I mean, that's in the literature, and we have to do it consistently. No one can show, and I don't want to do this. I mean, because that here is the projector, it becomes already clear that this is a spatial quantity, no? Because this h here projects on 3 surfaces, so one can show that k mu nu and nu is 0. The same holds for the other index. So that is k mu nu is like h mu nu, a purely spatial quantity. And we will again later only use spatial indices for that. Only now we have the space-time indices. And one can also show that k mu nu is k nu mu. That's not immediately obvious. So if you try to show this in one line, at least I cannot do it. But after some formulations, one can show it. It's in Wald's textbook, for example. You can also find it. I mean, that is symmetric. Now, what is the geometric meaning of that? Well, it's the covariant derivative of the normal vector. So let's having such a 3-dimensional sigma, of course, just in projection. And we are here at a point Q. And here we are, let's say, a point P. And here we have a normal vector n mu at Q. And here we have a normal vector, which is a normal vector field. Even if I call it only normal vector, it's a field P. So at each point you can erase the normal vector. So let's this. Now you can have at point P also a separate vector. You can parallel transport this one to here by the usual procedure of parallel transport in general relativity or in geometry. So you can have here another one that I call n mu tilde of P, which is the parallel transport of n mu of Q. Yeah? So it's clear, I mean, everywhere you have n mu, but you can also transport this to here. This is infinitesimal here, and then you have 2. And it's clear from this nabla that if n mu does not change, I mean, this k is 0. But if this n mu changes, then you get a non-zero. And that, in fact, k mu nu can be defined as a measure for this difference between the two. So k mu nu is a measure for the difference between n mu at p and n mu tilde at p. And so it gives, so to speak, the embedding curvature, because this is the three-dimensional hypersurface, and if this is curved, yeah, it means you look from it for outside and you see that the normals then change. No? So this is so-called extrinsic geometry, because it's not what the little ants that are here measure on the three surface, but what you see from the outside. And so K mu nu is called extrinsic curvature, or for historical reasons also second fundamental form. In physics, we usually talk about extrinsic curvature. This goes back to Gauss, no, who introduced these concepts for surfaces, for 2 dimensions, and who called the metric as the first fundamental form and this extrinsic curvature as the second fundamental form. Because he was the first who had this insight that you should distinguish between intrinsic geometry and extrinsic geometry. Before Gauss, everything was somehow extrinsic, or people had looked at geometry from outside as embedded, but not from inside. And Gauss showed that one can have a geometry purely intrinsically. There's no need even for an embedding. So again, this here, I mean, this is flat, certainly, Euclidean geometry. And if you make it to a cylinder, then again, the cylinder is intrinsically flat. I mean, all triangles add up the angles to 180 degrees, for example. But from outside, it looks different. No? So this has a 0 K mu nu, but this has non-zero K mu nu. So same intrinsic geometry, but different extrinsic geometry. But for the canonical formalism, we needed two. Okay, you can further show. Now I go to the spatial notation, because it's a spatial quantity. Yeah, it's orthogonal to n. So let's just go to the sigma itself, and having AB with 1, 2, 3. One can show, this I will not derive, but one can show that this is, how do you show that? You show that from the definition and using here this decomposition into lapse and shift. 1 over 2n, and then you have HAB dot, so d over dt minus dA and b minus dB and a. So what is that d? This is the covariant derivative with respect to the three-dimensional metric. Now, with respect to the four-dimensional metric, this is our old nabla, but we also have now three-dimensional geometry, and there's a different metric, and you can have a different covariant derivative, which we denote by that. No? So that is three-dimensional covariant derivative. Yeah, so, of course, we set speed of light equal to 0. Otherwise, this would be HAB over C dt. So, I mean, so that K has the dimension here 1 over length. But it can also have 1 over time, depending on your units. But you see, that is, okay, if you forget for this, that's something like the velocity of HAB. Yeah, forget about this additional term. And about this, then KAB is basically HAB dot. Yeah, and so going back to this old analogy with Q's, no, and P's, then this KAB would be the analog of the Q dots of the velocities. And so, okay, then we have to have something like m times Q dot, which is the momentum. But you see, this is the analog of the velocity, the second fundamental form. Just as a remark, I will not need it But one can show, for those of you who are geometrically inclined, this is minus the Lie derivative with respect to the shift vector of the 3 metric. Also has a nice then geometric interpretation. We also defined the trace of K as KAB times HAB. And in simple models of cosmology, we do this in chapter 8. Cosmology, it just becomes the Hubble parameter, for example, no? Because it gives you, in space-time, it gives you the expansion. Then this embedding gives the expansion of the 3-dimensional surface. So if you have the expanding universe, then you have the Hubble parameter, which is A dot over A, and this is basically this here. But we will come to that. Okay, let me, before proceeding, give you maybe a bit more insight into that, and also going back to Gauss, who pioneered the field in 2 dimensions. And in Gauss had proven many important theorems, as you know, but there is one theorem that he himself denoted as the distinguished theorems. I mean, the herausragendes Theorem, which is so important that even for his other theorems it's important. And this is the famous Theorema egregium. Theorema egregium. And that's the following. It's for 2-dimensional surfaces. So what he showed was that, I mean, so 2 surfaces. Okay, in our notation, I write it with the Riemann tensor. Of course, he did not have the Riemann tensor. Riemann later gave his habilitation talk where he introduced this, but not when Gauss had proven this. So the 2-dimensional Riemann tensor has only one independent component except for the symmetric permutations. No? This is that you only have 2 indices, and okay, if 2 are the same, then it's 0, so everything can be related to that. And he showed that this is equal to K11 KT2 minus K21 K12, which you can call the determinant of the 2-dimensional extrinsic curvature, or you can write as the 2-dimensional determinant of the metric. So this is the determinant of HAB times what he called kappa 1 and kappa 2. These are the so-called principal curvatures of surface theory. Now, if you have a curved surface like a soap bubble, so then you have 2 orthogonal directions that are called the principal curvatures. And kappa 1, 2. So these are the principal curvatures. Hauptkrümmungen in German. They are orthogonal to each other, and they characterize the minimal and maximal curvatures that you have. I mean, the directions of minimal and maximal. And yeah, this we can also write here, because it's 2-dimensional, as a 2-dimensional Ricci scalar over 2, because there are no other possibilities. Yeah? There's just one number times the 2-dimensional metric. So all in all, you get then here these 2 together, that the 2-dimensional Ricci curvature is twice this principal curvature. No? So, and this egregium, this distinguished theory, means that you really have here a relation between the intrinsic geometry, which is from the Riemann tensor and Riemann Ricci tensor, Ricci scalar, and the extrinsic curvature, which from outside gives you the curvatures of the surface, no? As embedded in space-time. So this is the connection between intrinsic and extrinsic geometry. And it's And it holds in this form because of a property of the embedding space, because in Gauss' case, of course, everything is embedded in flat three-dimensional space. If you were to embed it into a Minkowski version, so embed a surface into a Minkowski spacetime, you would get here a minus sign here. So this contains information about also the embedding space. And so Karel Kuchasz calls this theorema egregium that the following, that the law of the instant that you can derive from this, the dynamical law of the instants means something that is at t equals constant. Now going back, of course, to the 3 plus 1, not going away from Gauss. And this refers to space-time, and this means in this case the flatness. I mean, in this case, flatness of space-time, of space, in Gauss' case, space or space-time. So you cannot choose this independently. I mean, if you have this something embedded in some bigger space or space-time, then information about the geometry of this bigger one is encoded here in that. And it has this form because Gauss embeds everything in three-dimensional flat space. But if you embed it in something else, then you get a different relation, which we will see then, because this will play a major role in the canonical formalism. It will be called there the Hamiltonian constraint. And the Hamiltonian constraint is just this generalization of Gauss' theorema egregium. Yeah. So the analog, well, I should write it here because it belongs to here. So the analog of, say, the star in 3 plus 1 dimensions is k squared, so the squared of the trace of KAB minus KAB plus the three-dimensional Ricci scalar is equal to the 0. That's again a relation that combines intrinsic geometry, which is here the three-dimensional Ricci scalar of the three-dimensional surface, with the extrinsic curvature. So this corresponds here to the theorema egregium. And one can show that, I cannot do that in the detail because we have principle now to make a 3 plus 1 decomposition of all geometric quantities of the Riemann tensor, the Ricci tensor, and so. I mean, this was done by a basically Italian physicist in the 19th century, Codazzi and others. So they made this formulation after Riemann had invented Riemannian geometry. So they came up with generalizing Gauss's theorems to the Riemannian case, so to higher dimensions. And this is often called Codazzi or Gauss-Codazzi equations. And yeah, it takes some time, you can imagine, to do that, but it's not needed here. I mean, if you want to check the details, you can read this step by step in the books, or you can just refer to differential geometry as a result of differential geometry. I mean, in physics, we do not have to rederive all mathematical results. So that's here so that would correspond here to that in a sense. And one can, so if one does this 3 plus 1 decomposition, one can show that this just corresponds to the G00 equation, component of Einstein's equations in vacuum. No? So 00 component of Einstein field equations. in vacuum. Yeah, because we have not yet add matter. It is just pure geometry. So later we will add fields, then you will have also other terms. But for pure geometry, that's it. And it's what we called so far a constraint or Zwangsbedingung, because this does not contain second time derivative. Yeah, it contains also, I mean, contains no time derivative at all, this here. And this here contains as one, well, yeah, okay, you see it from here, contains also only first time derivatives. So, but for initial value problem, you have to specify the initial value and the initial time, no? Because we have second order equations. And 6 of the 10 Einstein equations are of the second order, but 4, and this is the first of it, they are only of first order. So they restrict the freedom you have to specify q and q dot at the beginning. It is like as in Newton, you cannot have, I mean, the initial position and velocity arbitrary. Of course, in Newton you can, but here you cannot, because q and q dot have to fulfill a relation. They are constrained. And you have seen constraints last time and 2 weeks ago, and here we have already here now a signature of the constraint. Maybe I will switch on the light. Yeah. So that's very important. And okay, this is G00. And in 3+1 dimension, we also have many, not just this one. So this is the analog, but there are also 3 new constraints, and this is G0A is also a constraint. And the 19th century mathematicians have shown that this is a dB. Well, they have not discussed, of course, the Einstein tensor, but they have discussed the following relation later. We identified so that this is dB kBA minus dAk is 0. And this is often called the Kodazzi equation. So in Riemannian geometry, you do not just have the theorema equilibrium, you have these 2 relations. Yeah, so what about the initial value problem in general relativity? Also, this is what the numerical relativists do with their supercomputers. So you have your sigma, and you specify HAB and KAB on sigma, but satisfying these constraints. And then there's a theorem that shows that there exists exactly one globally hyperbolic space-time which satisfies the Einstein equations and which has a Cauchy hypersurface where these initial values hold. That's very important. Maybe it's so important that I write it down. So initial value problem. Problem of GR. So specify HAB, KCD, on sigma, okay, satisfying the constraint, satisfying the constraints. Then there exists exactly one globally hyperbolic space-time which fulfills the Einstein equations. Now in vacuum, I mean this can be generalized, but now it's vacuum, Einstein equations in vacuum, and which has a Cauchy hypersurface, with values A, yeah, the initial values H, A, B, and K, C, D. Yeah? And so what the numerical people often do then is they give this, they calculate, and then the constraints must be fulfilled, of course, everywhere. And then they check the accuracy of the code by calculating the constraint and checking that it's close to zero within the accuracies. So that you can use the constraint also to check your numerical procedure. This is non-trivial, yeah. So because this is here, space-time is not yet constructed, yeah. So you just have a sigma. It's not that you start with a sigma in a space-time, a sigma. Then you can construct a space-time. It's not like in electrodynamics, where, for example, on a sigma you can specify your vector potential and your electric field, and then you can solve Maxwell's equations. Also there in electrodynamics you have a constraint, namely Gauss' law. So even there you can have you cannot specify the vector potential electric field, which are conjugate variables freely. I mean, nabla E must be zero in vacuum, and this has no time derivative. So nabla E must be zero all the time. No? And this is a constraint. Yeah. There are nice so-called interconnection theorems. So there's also the theorem I'd only mention. So validity of the constraints on every hypersurface. Then you can show that also that the remaining Einstein equations must hold. That is, you cannot proceed from one hypersurface to the other by having the constraints, but not having then the other Einstein equations, which are really the dynamical equations because they have second time derivatives proceeding. So there's a strong interconnection between say, as Kuhash called the law of the instant and the dynamic law, that what is going on in at constant t on sigma and what is going on in space-time. And it holds also the opposite. So if we have this equation and the constraints hold on one hypersurface, then they hold on every hypersurface. And I must say that similar theorems also hold for electrodynamics, which I will not mention. So I hope the procedure is clear. Now we have identified our q and also our velocity. So the momentum is still lacking, and the momentum then we define as dl over dq dot, and dl is then from the Einstein-Hilbert action. Recall the Einstein-Hilbert action. So 16 pi g times s eh. You have the integral over the 4-manifold d4x square root of minus g, 4-dimensional Ricci scale. So without 4, it's just 4 dimensions. For 3, I explicitly indicate 3 minus 2 lambda. And we add here the usual surface term that is not always discussed. I think I only briefly went over it in the relativity class. But if m has a temporal border, then we have here also a 3-dimensional term, square root of h, no? 3D determinant of the 3 metric, and a trace of the extrinsic curvature. So why that? So in case you have not seen that, the point is, without that, the old Einstein-Hilbert action also has second time derivatives here for the Lagrangian. That's not a problem by itself, but physicists are conservative, and in mechanics you have usually L that depend only on Q and Q dot, but not on Q double dot. Now you can of course make a variational principle with Q double dot, Yeah, but if you have the usual Euler-Lagrange equations, you have L of Q and Q dot. Now you can observe that this has second time derivative of the metric, but they are linearly occurring only. So you can make a partial integration and put them to a surface term, and if you want to avoid them, you just add the negative of that surface term. So it's just a trick, I would say, for mathematical convenience and for the pleasure of the physicists who want to apply what they have learned, the mechanical formalism, to only have first time derivatives. Actually, already Einstein has done that in 1916, though not in such a short notation here. Later it was rediscovered in 1978 by Gibbons and Hawking. This is why it's called the Gibbons-Hawking term. But it was it was known long ago. But Gibbons and Hawking really gave that form here, and it's much okay. It's better understandable than the old Einstein calculations, which are explicit with many indices, and it's hard to understand. Yeah? So this has only first time derivatives. So one can then show, and this is what Arnovet, Diesel and Miesner have done, and what you get when you apply all these decompositions into three-metric and second fundamental form of these quantities, now using these Gauss-Codazzi equations and the like. As I said, this is classic geometric material that you can just take over, or you can, if you like geometry, spend maybe a day or two just to go through it. Anyway, but this is, so one can show, so 3 plus 1 decomposition, that this is can be written as the integral of m. Then instead of d4x, I write dt d3x. And now the lapse comes, n times square root of h. Actually, this can be shown here to be n directly n times square root of h, from that form that we had with the matrix. And then we have KAB minus k squared plus 3r minus 2 lambda. Yeah, so we can also write this equivalently as follows by introducing a short notation, integral m dt d3x n, and then we have g a b c d k a b k c d plus square root of h 3r minus 2 lambda. And this is called the ADM action. It's the ADM form of the same action, but written in different variables. So let's call it SADM. Arnovet, Diesel, Miesner, who end of the 50s introduced this 3 plus 1 decomposition into the physics literature. So, but of course it comes from the Einstein-Hilbert action. So that's the covalent formalism. This is what you use when you calculate a path integral, say. And this is then what you use when you do canonical quantization or formulation. I have assumed that there is no spatial boundary so far. I will briefly say later something about if you have a spatial boundary, then there are surface terms from space also, which are not important for our purpose. Yeah, this here is something that depends on the 3 metric. Explicitly, it's given by square root of h over 2. Yeah, and then you have these things that you have in relativity. Yeah, these combinations of indices plus h, ad, hbc minus 2 h, A, B, H, C, D. And it's called the de Witt metric. Because Bryce de Witt introduced it in his pioneering papers on canonical quantum gravity in 1967. So this was not yet done by Arno Medeser-Miesner. So de Witt, he made the quantization, and for that he also rewrote many of the classical expressions. So you see here that has now or is close to a form that you are familiar from classical mechanics, because remember the KAB, they contain the HAB dot. So this is something like the Q dot squared. And in principle, this is what you know as 1/2 m Q dot squared minus potential. It's just that here the things are a bit more complicated. So S ADM can be written as integral dt d3x of a density Lg, and this has the form kinetic energy minus potential energy. This is what we wanted. No? We wanted this to be back in the old world of classical mechanics and field theory, to develop then a Hamiltonian formalism and doing classical Hamiltonian equations, but then also quantize. I should also mention there's of course an inverse to the de Witt metric with which lower indices, but I maybe don't write it down right now. So the here you have the GABCD, KAB, KCD, and so this contains here HAB dot, and the potential term is then here minus square root of H, and you have 3R minus 2 lambda. And this is the starting point for the canonical formulation and the canonical quantization. So in a sense, this is the preparation that we needed now to really start what we wanted to do. So then we can apply the game, the canonical formalism. So we define the momenta. The momenta are dl over dq dot. Now what are the q's? Okay, we are the HAB. But if you think in terms of the form metric, we also had, in principle, have lapse and shift. But lapse and shift come here only without time derivative. No? The lapse is just here, multiplies everything, and the shift is here, hidden here, but it has no time derivative. So pedantically, we also include them into the canonical formalism. Canonical formalism. So let's have Pn is then dLg over dn dot and is 0, and also Pa, which is defined as dLg over dna dot is 0, and because they're 0, there are also constraints. Okay, you see here, these are constraints. So in Dirac's notation, I should write it here, this with this notation. But I think it's clear from the context. So there's a constraint, and they're called primary constraints. Dirac, or it was maybe Bergman who introduced this notation, primary, because you do not yet need the equations of motions for that. It's just the definition of the canonical momenta by themselves lead to a constraint. For those of you who know the canonical formalism of electrodynamics, there is a similar thing, P0, which if you have the electromagnetic Lagrangian, and you differentiate with respect to the zero component time of the vector potential, then this is also zero. Because A0 is here only undifferentiated. Now, but of course now there are then the real momenta, and so P, I call them PAB. Sometimes also pi, I mean it's different in the literature, is so dLg over dHb dot. And the result, if you do that, I mean, where's the HAB dot is here, no? And so you just have to insert our expression that I wrote down and differentiate with respect to this. So, because there was a question, maybe I write it down again. That's this here. And what you get then is 1 over 16 pi g, g, a, b, c, d, k, c, d. Okay, it comes the same from the both components, and then you get this. So that's the canonical momenta. I mean, you can also write this as by inserting here this explicitly, you can also contract the indices, and you have here square root over 16 pi, square root of a 16 pi t, and then you just have k ab minus k times h. So that's the canonical momentum. Now we are complete. So that's the generalization of what you know from classical mechanics, that you have m is m q dot. In relativity, the HAB dots are hidden here, and that's the momentum here. And so I emphasize that here explicitly the gravitational constant enters, in spite of this having vacuum general relativity. And vacuum general relativity, the Einstein equations, there is no gravitational constant on the right hand side, because it's just capital G mu nu equal to 0. But in here, when you do canonical formalism, the G comes, and this will be relevant in the quantum theory, because the quantum theory you quantize P's and Q's, which means that the gravitational constant will enter vacuum quantum gravity, even if it does not enter classical vacuum gravity. It's like when you have, say, free fall of neutrons or so. Classically, of course, the mass does not enter, because of equivalence principle. But it enters when you have a wave packet. I think I explained that in my very first lecture, because there you have p squared over 2 times m in the denominator, and then coupling to gravity with m in the numerator. Okay, so this is explicitly occurring. Because here, of course, you have it here in the action. Of course, if you just make classical physics, then you vary this and set it to 0, so it does not really matter what you write here. You could write whatever you like. But if the action is defined by this and you have a momentum, then it matters, what you have here. This is why G enters. Okay, here, this you can, of course, also solve with respect to Q dot. So, I mean, Q dot is P over M. And of course, a similar thing you can also do here. You can solve this with respect to HAB dot, which I leave as an exercise if you like. It's not difficult. HAB dot, because this is contained here, is this term. And then you have P AB minus 1/2 P HAB. Now this is the trace, so this is H PAB, HAB, and then you have plus DA and B plus DB and A. No, so you see, okay, this is of course more complicated, but so from the concepts, very familiar, I would say, when you recall classical mechanics or classical field theory. And that was also the intention of the pioneers doing that in this way, because the covariant formalism of general relativity was something really new and with the action not comparable to the forms you had in classical mechanics. Now, because P and Q are the this P and the three-metric are canonical conjugate. So this here, and then you have the three-metric. So they obey a Poisson bracket relation. Like here you have Q P is equal to 1. Well, sometimes it's defined so that it's -1, but not the Poisson bracket. And then you have here also the Poisson bracket HAB of X. This means a three-dimensional X. I don't write vector signs. Everything is now three-dimensional. PCD of Y. Okay, then you just have here the Kroneckers. You symmetrize them to respect the symmetries of the left-hand side. And then you have here delta of X minus. So delta function here, but Kroneckers with respect to discrete indices. So that's the Poisson bracket relation. And it's defined in the usual way. Like here you have the first you derive with respect to Q, difference with respect to Q, this with P, and then minus the opposite, and this just gives 1. And here you do it with respect to the three-metric and the momentum. So that's the fundamental Poisson bracket relation. Now we can go to the Hamiltonian. So I will finish on that blackboard. So let me start here that I have enough space. So the canonical Hamiltonian is found by the usual Legendre transform. You recall H is PQ dot minus L. And so you have here, this is PAB HAB dot minus LG. And of course, this depends only on the P's and the Q's, and not on the velocities. So this here has to put in here. Like in the usual case, you have the Q dot, you have to insert there. Okay, and what do you get is then the following. So then you get HG is 16 pi G times N times GAB CD PAB PCD minus N times square root of H over 16 pi G times 3R minus 2 lambda minus 2 and B dA PAB. And then you can find from this, what is the Hamiltonian density? Naturally, the full Hamiltonian you get by integration over space from the density. So you get from this then that I call just the full HT, which is the integral d3x HG, is then integral dx. Yeah, you see here there are two terms where the n is in front, and then there is something with I think maybe the brackets where this is in front. Now, so you can write this as n times a function which we call h orthogonal g plus then na. You can also raise the index times something that is called ha of g. And you see already from the notation we had before the Hamiltonian constraint and the momentum constraint, and they are constraints. Why? Because if you vary with these are Lagrange multipliers, because there's no time derivative. If you vary with respect to them, then you get that these two are zero. A canonical person would argue as follows. The canonical person would say, no, we have these primary constraints, and we have to demand that they be preserved. So the Poisson bracket, say, of Pn with h must be 0. And then you get just here 1, no, Pn from n, and then you can get 0. So that would be the canonical argument, but you can directly see here that because they are Lagrange multiplicators and they are, you vary with respect to them too, because they're actually part of the 4 metric, and they give you the constraint. No? So variation with respect to n and a gives the constraints. Yeah, and let me write them down. Maybe I write them how constraints. So I continue here. H orthogonal of G and H A of G, and this is 16 pi G times G A B C D P A B B C D minus square root of H over 16 pi G, and then we have 3R minus 2 lambda is 0 as a constraint. No? If I write it in this Dirac form, and this is just minus 2 d b p b, sorry, p a b is 0. So then these are in that case now the Hamiltonian momentum constraint, and we already had them last time, no, in the parameterized field theory, already in the particle cases. But here, this is now are the constraints in general relativity. And so this, the first is called the Hamiltonian constraint. And it corresponds to what we had, say, for the relativistic particle. This p squared plus m squared is equal to 0. And this here is the diffeomorphism, or well, these are 3, so it's a plural momentum constraints. And they correspond actually to what we have in electrodynamics, where you have Gauss' law. So this is also just the derivative of a momentum in electrodynamics. The A, the vector potential, plays the role of the Q, and the electric field the role of the momentum. Instead of A, you could also use the magnetic field. So you could also have magnetic field and electric field as the conjugate variables. And the electric field is constrained. It must obey in vacuum nabla E is equal to 0. That's it. No? And okay, the B must fulfill nabla B is equal to 0, but if you have the A, then this is already taken into account. Yeah, and in fact, this is here, in a sense, the generalization of Gauss's Theorema egregium here to 4 dimensions. Yeah, if you have the Hamiltonian equations of motions, that means you have HAB dot is Poisson bracket of HAB, and if you do that, then you get back here this equation that you have already found by hand, so to speak. So as before, and the new thing is, of course, what you get. PCD dot is PCD HT. Okay, this I don't write down. It's long and lengthy and not needed, so I don't have to write it down. But this one can show that this gives the remaining 6 Einstein equations. So we have this this is G00 equal 0. This is G0A equals 0. Well, this is G00 equals 0. And this is G0A equals 0. And this gives GAB equals 0. And then they really give the time evolution. So the remaining 6 you get really then from evolution. There's no constraints. I should at least write down what you get if you have non-vacuum. So non-vacuum case. So then you have H orthogonal as above, and you have here plus square root of H times the energy density is equal to 0. So this is T mu nu and mu and nu. Now the zero component of the energy momentum tensor adds here to the first and to the second. Okay, you have this here. And you get plus square root of H at GA, a current, and this is H a mu, T mu nu, and nu. So in electrodynamics, it's just the Poynting vector, which gives you the flow of energy in a certain direction. And if you have any other field, not electrodynamics, then of course you have similar terms. Because in Einstein's theory, matter is described by T mu nu on the right-hand side. And of course, the T mu nu you can also decompose into normal and tangential components. Normal with respect to n and tangential with respect to the projector. And then you get these terms here. So if you have, say, I have no time, but if you have, say, a scalar field or an electromagnetic field, if you like, this is a simple exercise. You can write down the Lagrangian and calculate here these terms. Yeah. So the last thing in the last 3 minutes is something interesting, conceptual, namely what Bayerlein, Sharp, and Wheeler called that 3 geometry contains information about time. So Bayerlein, Sharp, and Wheeler, John Wheeler, already in 1962, they had this often quoted statement, which you find in Misnerson and Wheeler. Of course, 3 geometry contains information about time, or is the carrier of information about time. What do they mean by that? And there's an important difference between gravity and, say, electrodynamics or other theory. And in gravity, okay, you have here, say, a sigma 1 and a sigma 2, and Wheeler writes this as, say, a 3 geometry 1 and a 3 geometry 2, but it's just the sigmas. And one can prove, or this conjecture, the proof holds with certain assumptions, but it's believed to be true, the so-called sandwich theorem, that those three geometries, they by themselves, they allow to calculate here the time separation in proper time for any observer to go from here to here. So they already determine the temporal distance between along any time-like world line determine the temporal distance along any time-like world between them. That whoever moves here from this to there either maybe just stay at rest and time goes or moves, then this by the sandwich theorem, this is already determined here. But this is not the case, say, in electrodynamics. If you have, so this is not, say, in electrodynamics or any non-relativistic theory where you have a fixed space-time. If you have a fixed space-time, then you have here B1, T1, say, and B2, T2. So these are magnetic fields. Then, I mean, you cannot calculate it. So if you give here the magnetic field and here you give the magnetic field, you cannot calculate the time difference between them. No? Or that's what Henri Poincaré called the Poincaré defect. If you have, say, in celestial mechanics, if you have a snapshot of celestial bodies at one time and you have a snapshot of those bodies at another time, but you don't know the time difference. So the question that Poincaré asked was, can you determine by Newtonian mechanics a time difference between the two snapshots? Yeah, and he answered, no, yeah, you cannot. I mean, you would have to need, for example, the energy or something like that, like a conservation law. This is called also Poincaré defect, because just from pure photos of two configurations, you cannot infer the difference. No? Also, if you look at the clock here, if you have two clock configurations, say now, and maybe if it shows a 5:45, you cannot infer from it the temporal distance. I mean, the clock may go wrong, and so you cannot trust it. No? You would need, in addition, say, the speed maybe of the pointer, or you have the total energy or not. But you can have this here in relativity. So from 2-3 geometry, you can infer the temporal distance. So, and this is what John Wheeler and Bayerlein and Sharp call that 3 geometry contains information or is carrier of information about time, and in Misonson and Wheeler they elaborate on that. So it could also be rephrased in the way that time is inextricably linked here with the dynamical degrees of freedom, in a sense. Yeah, and only if you make a approximation that you're maybe close to Minkowski space or something, then you can split up maybe time. Okay, then thank you for today, and next time we do the quantization.